Let us now discuss about aromaticity. For a compound to be aromatic, it has to follow some conditions. Let me say. So it should be cyclic. Point number one. It should be planar. See, when I say planar, all atoms involved in conjugation should be sp2 hybridized, right? sp2, trigonal planar, cyclic planar, and of course, it should have 4n plus 2 pi electrons. Okay. Now, this is what I call Huckel's rule of aromaticity. Right? These are the characteristics of an aromatic compound. It should be cyclic, it should be planar, and it should also have 4n plus 2 pi electrons. Some other. Aromatic compounds are generally diamagnetic. Within an aromatic compound, a kind of induced ring current sustains or is present. So it is also called diatropic. Okay. Aromatic compound sustains an induced ring current. Of course, because of the conjugation. So it is called diatropic. Okay. Diamagnetic, diatropic. One more interesting point. When an aromatic compound is compared with an open chain compound with the same number of pi bonds, the aromatic compound is highly stable. Again, because of the resonance. During which some amount of energy is lost, so becomes more and more stable. Because any system with less energy is more stable. Okay, with the same number of pi bonds or the same number of electrons, and this is very important. Now there is another category called anti-aromatic. See, anti-aromatic compounds are those which are cyclic, planar, of course, conjugated, the same as the aromatic compounds. Only difference is these have foreign pi electrons. So this is the basic difference. Cyclic, planar, conjugated. These are common to both aromatic and anti-aromatic. And when you actually see the stability of anti-aromatic compounds, and when the stability of anti-aromatic compounds is compared with those of the open chain compounds with the same number of pi electrons, are less stable. Okay. Anti-aromatic compounds are less stable than the corresponding open chain compounds with same number of pi electrons. Let me also tell you a reason, also tell you a difference between aromatic and anti-aromatic compounds. See, in case of aromatic compounds, the cyclic delocalization leads to stabilization. Of course, we have already seen that. But here, the same cyclic delocalization leads to destabilization. Okay. In case of aromatic, cyclic delocalization of pi electrons leads to stabilization of the system. But In case of anti-aromatic, the cyclic delocalization of pi electrons leads to destabilization. Okay. Now this is all about anti-aromatic. Only difference is these generally have 4n pi electrons. Now then, what are non-aromatic compounds? And what is the order of stability of these three varieties? Now, in this case, this may be cyclic. In just one word, I can say that if no single condition, I mean, if at all any one condition of aromatic and non anti-aromatic is not followed, then we say that it is a non-aromatic compound. But generally, this is where the problem lies. See, these are non-planar, and these need not be fully conjugated. I mean, conjugation may extend to a lesser distance. Okay, let us take examples. Now, before examples, let me give you the order of stability. See, the order of stability can be given as aromatic, then, of course, non aromatic, and the least stable, anti aromatic. Okay, now let us take some examples. Look at this. So, this is cyclopropyl cation. Cyclopropyl cation. Let me show you the conjugation thing. See, it may move this way. It may even move here, right? Simple. This goes here. Then this one loses. Of course, this one retains. So is a positive charge here. Then it goes here. This one loses, whereas this one is retaining. So a positive charge here, right? Now, overall, I mean, this can, of course, be given as I mean, it can be shown that the pi electron can migrate within this and of course has a positive charge. So therefore, this is aromatic, right? And of course, even the hybridization, if at all is checked, We know that the double bonded carbons are sp2, even the carbocation is sp2. So sp2 hybridization. Now supposing if the same thing is taken with a negative charge, look at this. Now what kind of a species is this? I can tell you that it has everything just like the previous one, but the point is it has 4 pi electrons. In this case, we have 2 pi electrons, which fits into 4n plus 2. Of course, here this n can be anything from 0. Supposing if n is taken as 0, it becomes 4 into 0 plus 2, 2 pi electrons. That means it fits into 4n plus 2 pi electron rule. I mean the Huckel's rule of aromaticity. Whereas when you go for this, you got just 4n pi electrons. I mean 4 pi electrons. 2 plus 2. So therefore, this is anti-aromatic. Okay. It is cyclic. It is conjugated. It is planar. But the point is it has got 4n pi electrons. So is anti-aromatic. Okay. Now, look at this. Now, coming to this. See, here also the hybridization of course, the pi bond, even that of boron is sp2, right? In this case, we can take it here because even boron will have a vacant p orbital. Can be shown this way. A vacant p orbital. That is the reason why we are considering sp2. So that no, if you got a vacant p orbital, you can accommodate the electrons. Now, these are the electrons that are coming to you so that the vacant p orbital can accommodate these electrons. Now, it is this. But at the same time, boron gets a negative charge. Okay. Now, this is aromatic. It has got 2 pi electrons. Okay. Next. Let us take this example. How about this? Very clear. It has got 4 pi electrons. Therefore, anti-aromatic. Now look at this one. See, when this kind of a thing is considered, so this is cyclopropanone. See, because oxygen is more electronegative. Consider it this way. Oxygen gets a negative charge and carbon gets a positive charge. This has become aromatic, right? Consider this. It has got 2 pi electrons. Of course, the positive charge goes on, makes rounds in the ring. I mean, it undergoes cyclic delocalization. And remember, because it has got 2 different charges, let us also say that it will have high dipole moment. Even this also is an important factor which is generally pronounced in case of aromatic things. Next. It's becoming more and more interesting. Check this out. Different examples. That's it. See, when this is treated with, perchloric acid, the strongest of all acids. Look at what has happened. Of course, the same thing. O minus, but that O minus abstracts a proton from this acid. Then this will become O minus and H plus, but still there is a positive charge. Now look at this area. Right? It's an aromatic salt. You got a plus charge. You will also have Cl4 minus along with it. This is an aromatic salt. Okay. Next. We can also consider halides. Take silver nitrate. Now we know that this can actually form silver bromide. Right? Now look at what happens. See, from this, we can actually remove AgBr. then what happens is you get a positive charge. Yes, it has become aromatic. This one, but silver bromide, of course, is precipitated. This is again an aromatic salt. Okay. Now, now if you consider this, say this is cyclobutadiene, right? It is a cyclic, it is conjugated, it is planar, since all the carbons are sp2 hybridized. But only problem is, it is having only 4 pi electrons. 4 pi electrons, therefore, anti-aromatic. Okay. Next. Now the same thing, if at all, is converted into some cationic and anionic species. For example, if it is made into a dication, now even here also we will have vacant p orbitals, isn't it? We just have, let me write it as cyclobutynyl dication. So it has got only 2 pi electrons, fits into 4n plus 2, so is aromatic. Okay, let us consider some more. Now if the same thing is made into dianion, minus minus, nothing but 2 electrons, 2 electrons. Conjugation is possible, you got electrons, it has 6 pi electrons, cyclobutynyl dianion. It has 6 pi electrons, therefore aromatic. Fits into 4n plus 2 with n is equal to 1. Now, look at this. See, this is cyclopentadienyl cation, right? Of course, all are sp2 planar cyclic. But the problem is, I mean, the thing is, it has only 4 pi electrons. Therefore, it's anti-aromatic. No problem, you can say anti-aromatic. Now, let us just have boron here. Now, even here also, instead of having a positive charge, we got a boron, which is, of course, of sp2 hybridized and has a vacant p orbital so that it can accommodate the pi electrons that come due to conjugation towards it. Therefore, even this also is anti-aromatic, right? Now, consider a nitrogen. Now, this is aromatic since it has got 6 pi electrons. Okay. Now, this nitrogen is of sp2 type, isn't it? But if the same thing is considered with a negative charge, the same cyclopentadiene, if it is taken with a negative charge, then so this is cyclopentadienyl anion has got 6 pi electrons. Therefore, it is aromatic, right? So this is how can take number of examples.